I, Dr. Jitesh Shinde, welcomes you to my channel Learning Made Easy. In this session, we shall be seeing signed binary numbers with more emphasis on sign magnitude approach. Unsigned binary numbers. An unsigned binary number has no arithmetic sign and are always positive. Example, age, memory address, weight and currency. In the last two sessions, I had covered number system and conversion of number system. All the examples which we had dealt in those two sessions were assumed to be belonging to the category unsigned binary numbers. Range of unsigned 8-bit binary integer. For example, 4-bit instead of 8-bit, let's see the example of 4-bit. If n is equal to 4. Okay, so what is the minimum value we can represent in 4 bits unsigned binary number? The answer is 0, 0, 0, 0. In decimal format, we can write 0 to the base 10. This is unsigned binary number 0 in n equal to 4-bit representation scheme. Maximum number we can represent 1, 1, 1, 4 ones. Okay, this in decimal number system answer is 15. 15 to the base 10. In hexadecimal format, answer is 0 to the base 16 and this is F. Okay, how 15 we had obtained? Here we have used the knowledge of 8, 4, 2, 1 code. 8 plus 4, 12, 12 plus 2, 14, 14 plus 1, 15. Thus 15 decimal equivalent in unsigned binary format, answer is 1, 1, 1. Okay, n equal to 4. Thus in n equal to 4 unsigned binary format, the least number we are getting, minimum smallest number we are getting is 0, largest number we are getting is 15. In generalized way, okay, in generalized way we can write the range is 0 to 2 to the power n minus 1 minus 1. Is this formula correct? Let's check it out. N equal to 4. So n equal to 4, if we substitute here, what will be getting? 2 to the power 3 means 8. 8 minus 1, 7. No, this formula does not work here. So we need to modify the formula. Okay, is this formula fitting here? Let's check it out. N equal to 4. N equal to 4, if we substitute here, what will be getting? 16 minus 1. It is evaluating to 15. Answer is 15. Thus the generalized formula to represent n-bit unsigned binary number, the generalized formula is 0 to 2 to the power n minus 1. Same thing has been written here. N-bit binary integer generalized formula is 0 to 2 to the power n minus 1. Similarly, for n equal to 8-bit binary integer, the range is 00 to FF in hexadecimal format, 0 to 255 in decimal number system. Signed binary numbers. The techniques used to represent signed binary numbers integers are signed magnitude approach, 1's complement approach and 2's complement approach. In this session, we shall be concentrating on signed magnitude approach only. Let's see. In signed magnitude approach, MSB of the given nth bit binary number, that is MSB bit. MSB bit represents the sign and the remaining n-1 bit directly gives the magnitude of the number. For example, say 9. Okay, say we are using n equal to 5-bit representation scheme. Okay, plus 9. If I want to represent, this is equal to represent plus 9 decimal in n equal to 5 bits sign magnitude using sign magnitude approach represent in signed binary number format. So MSB bit represents positive. Okay, since the number is positive, so sign bit, that is the MSB bit, will be writing here 0. Remaining 4 bits, remaining n minus 1 bit, that is 4 bits will be representing the magnitude. Let's use here the knowledge of 8421 code. Okay, 8 plus 1, 9. Okay, only 8 and 1 are involved in the addition. The corresponding bits has been placed 1. 4 and 2 not involved in the addition, so place 0, 0. Thus plus 9 in signed binary number format using signed magnitude approach, the answer is 0. Sorry, the answer is 1, 0, 0, 1. This will be our answer. Suppose that we want to find minus 10 decimal in signed magnitude approach format. Okay, same. Number is negative, so sign bit here will be 1. If number negative, sign bit is equal to 1. Number positive, sign bit is equal to 0. Remaining 4 bits will represent some magnitude, so answer will be 1, 0, 0, 1, remaining 4 bits. Thus, plus 9 decimal in signed binary number using signed magnitude approach format, answer is 1, 1, 0, 0, 1 to the base 2. So this is the approach. Further examples, plus 7. The number is positive, so 0. Remaining bits represents the magnitude. Here we are using the knowledge of 4 to 1 code. 4 plus 2, 6, 6 plus 1, 7. So the answer here is 1, 1, 1 to the base 2. Okay. Minus 7. Number is negative. So MSB bit 1. Remaining bits represent the magnitude. So 1, 1, 1. Plus 127. Plus 127 we need to write here. Okay. Here we can use the knowledge of 32, 16, 8, 4, 2, 1 code. Or you can follow the approaches discussed in my previous tutorials on based on number systems. Okay, here I am following this logic 64, say 32, 16, 8, 4, 2, 1 logic. Okay, how many bits are there? 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7. Okay, so all the bits 1 means 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1 will gives the magnitude 1. So this has been placed all once. Number is positive, this bit is 0. Minus 127, number is negative, so MSB bit is 1. Remaining bit represents the magnitude of the number. Plus 0, number is positive, so 0 has been written here. Here n equal to 8 bit representation scheme being used, so remaining 7 bits are 0. Minus 7, MSB bit 1, remaining bits represents the magnitude of number. Further, from this example we see that there are two representation scheme for 0. There are two representation scheme for 0, but 0 is neither a positive number neither a negative number. So we can consider this as one of the drawback of the signed magnitude approach used for the representation of signed binary numbers. One of the drawback. Range. The range of n bit signed magnitude integer. For n bit in generalized way, the formula is minus 2 to the power n minus 1 minus 1 2 plus 2 to the power n minus 1 minus 1. Let's see how it comes. Say we are dealing with n equal to 4. N equal to 4 representation scheme being used. Okay, bits are say B3, B2, B1 and B0. Using 4 bits, okay, we want to represent signed binary numbers. Okay, say smallest number is minus 7. How we can represent minus 7? Number is negative. So this will be 1, remaining bit 1, 1, 1. Plus 7. So this will be 0, remaining bit 1, 1, 1. Okay, so in generalized way, the formula is, okay, let's try to find the formula. 2 to the power minus I am writing, what should be getting the answer? 7. Okay, if we substitute 4 here, what will be getting? 16. 16 minus 1, 15, not hitting. So here what we need to append here in the formula? 2 to the power n minus 1, okay, so minus 1, 2, the range is 2 to the power n plus 1 minus 1. This will be the range. Thus the generalized formula to represent signed binary number, to represent the range of a signed binary number using sign magnitude approach is minus 2 to the power n minus 1 minus 1 to plus side, positive side, 2 to the power n plus 1 minus 1. Same has been written here. It will be more clear from this table as well. 0. This table also shows that for the representation of the 0, there are two schemes. Plus 0 means 0, 0, 0. Minus 0, answer is 1, 0, 0. Okay, means there are two representation scheme for the 0. Plus 1, 0, 0, 1 represents the magnitude, number is positive, so 0 has been represented here. Minus 1, 0, 0, 1, 1 written here. Okay, so this table gives us the idea, okay, how the range is minus 2 to the power n minus 1 minus 1 to plus 2 to the power n minus 1 minus 1. Okay, in decimal, if we substitute n equal to 4, the range we are getting minus 7 to plus 7. Drawback. Complexity in design. The first drawback is complexity in design. Here, if both the numbers are positive, the result will also be positive. Circuit will be simple. Okay, if you are designing an application in which the inputs are based on sign magnitude approach, okay, so if sign same, if both the inputs are having same sign, circuit will be simple. Okay, plus plus result positive, minus minus result minus. But if the two numbers are having two different signs, then there the complexity will arise. This will increase the complexity of the hardware in the designing process or in the algorithmic process. That is, to design a digital logic for the addition of two signed numbers, the circuit must examine the first sign of two numbers. If the two numbers are of same sign, it must add the magnitude and give the result with the same sign the two number has. Okay, less complexity. Complexity arises when if the signs are different. If the signs are different, it must compare the magnitude and subtract the smaller from the larger and give the result with the sign of the number having larger magnitude. If the signs are different, there the complexity will arise. The number which is having largest magnitude, that sign will come here in the result. Okay, so while designing, here one adder will be required, one comparator circuit will be required. Thus here the complexity of the design is going to increase here. Another drawback of the sign magnitude approach is confusion in the representation of 0. Okay, for plus 0, the representation scheme is 0, 0, 0, 0. For minus 0 in n equal to 4-bit format, the answer is 1, 0, 0, 0. Okay, so another drawback, okay, the two representation for 0 creates ambiguity in the representation scheme. These are the drawback associated with the sign magnitude approach. Thus, in this session, we have learned, okay, we have gone through unsigned binary numbers, followed by types of signed binary numbers. Means we have seen the approaches which can be used to represent the signed binary numbers: sign magnitude approach, ones complement approach, and twos complement approach. In this session, we had discussed in detail sign magnitude approach, representation scheme, its advantage and drawback. Thank you.